take some time to
Sure. No.
Is the pointer working?
Okay. Okay. Yeah. So while it is loading up, right? Just a clarification. I'm not a professor. I have a PhD, but I'm not a professor. And you will see when I talk that, I'm far from being a professor. And second thing is that this is not a research talk. I'm not going to really talk about any of the research that I'm going to do. It's going to be a very simple introduction to use of probability in computer science with very simple examples. I'll not assume any background, as long as you know what expectation is and what a random variable is, you should be fine. I'll ask questions. I think like you to answer. Okay. Okay, so that's the title. Some very simple examples. If there are any graduate students, master students, there is nothing here that you are going to learn. And as I said, the idea would be to give you very simple examples, and hopefully each of the example is powerful enough to show you that very simple ideas from probability can give you very striking results in computer science and related fields like combinatorics. Okay. It has a lot of applications, especially if you are working in theoretical computer science, machine learning, optimization, and so on. So before that, right? So suppose I asked you to just compute the value of pi. Just give me an estimate, a computational way of giving me an estimate for the value of pi. How would you do it? You can raise your hand and okay, so that's one way. But suppose I want you to kind of give me an estimate through some kind of a, an experiment. But how do you do it? You don't know that's the value of pi, right? Yeah. Okay, so that's one way. Yeah, that's an analytical way. Just an estimate, suppose I asked you to do an estimate, right? Yeah, speak up. Maybe you should just think about the topic that I'm talking about. Okay, I'll draw a simple diagram. Let's hope some of you can think about this, right? Yeah, exactly. So that's one simple way, and that's the kind of things that we are going to do. Okay. So there are different events that you actually suggested when you gave the solution for that. That's the kind of things that we are going to do. Okay. So here is the first problem that we are going to look at. Okay. So it's a very simple thing. So this is about estimating independent sets in a graph. Okay. I assuming that all of you know what graphs are, correct? Do you know what is an independent set? Correct. Yeah. So suppose I give you a graph, okay, and just believe me when I say that computing so when you are looking at independent sets in a graph, ideally you want to look at as large a set as possible. Okay, you want to pick as many nodes from this graph as possible which are independent. Okay, but it's a very difficult problem. Okay, but there's an easy way to get some estimate. Okay, it's not a very good estimate, but it's still a useful estimate for certain class of problems. Okay, so here is the problem. So you have a graph, right, and each vertex in the graph has a degree dv. Okay, and my claim is that if you look at this graph and you look at these parameters for each vertex v, the size of the largest independent set in this graph is at least this much, okay, which is 1 divided by dv for all the v's. Okay, and you can see that this is actually a very useful thing. If you look, can you think of let's say a cycle? What's the size of independent set in a cycle? N by 2, right? And you get that if you just plug into this, right? Similarly, you can do this exercise for a tree and you will again get the optimal result. Okay, so this is a fairly powerful result, not always useful but useful in certain settings, and I'll show you how you can actually prove this statement using very simple probabilistic experiment. Okay, so what we are going to do is we'll just consider any random permutation of these vertices. Okay, there are n vertices in this graph. Let's just order them randomly from as v1, v2 to vn. Okay, and we are going to now construct an independent set. Okay, the way we are going to do is, obviously we are going to start with an empty set, and at each step what we do is, let's say for in this case we will start with v1, we will pick v1 to be part of our independent set. We can do it, right? We have not yet picked any vertex, so this can definitely go into the independent set. Then what we are going to do is we are going to remove all the neighbors of the vertex that you pick from S. Okay, so S is the set of candidates that you have. Initially all the vertices are there in the candidate. Whenever you pick a vertex V, what you are going to do is you are going to remove all its neighbors from S. Okay, and then when you come back next, you will again pick the vertex with the lowest index. Okay, and you will add it to I. So is this an independent set? That the set I that you are going to be left with at the end of these iterations? Is it? Why is that? Okay. Yeah. Okay, so I is an independent set. So what we are going to do now is we are going to get an expected size of this set I. Okay. So you consider a node V, okay, and we will associate an indicator variable IV, which indicates whether the node belongs to I or not. Okay, and the question is, I'm going to say the probability that V belongs to I is its expected value. Okay, so what is this? So look at any vertex. When is it likely that it will be included in the independent set? When none of its neighbors occur in the previous to it in the order, right? And that happens with just a probability 1 over dv, right? So that's what you get, right? The expected size of I is the expectation with which each of these vertices is going to be in the independent set, and this is just nothing but this, right? So this is one example of use of probabilistic technique in computer science. Okay, so we'll move on to the next example. I don't know whether this is of interest to you, or if you find any of this not interesting, let me know, or if you are finding any of this not clear, let me know so that I can explain it to you clearly. Okay. So we'll next look at this other example, which is called reservoir sampling. Okay, so this is again a very powerful example, but which just requires very simple techniques, and this gets used a lot when you are trying to do streaming computation, right? Suppose you are looking at a router data that comes at a large internet service provider's router, or if you are looking at a massive database and you are just doing a scanning of the database, right? So you are looking at a large stream of elements, and you want to maintain a sampling strategy. Okay, what it should do is that at any given point in time, it should maintain a sample of k elements. Okay, but since this is a stream, right, I want these samples. So when you have seen first k elements, you will have all those k elements in the sample, correct? And as you proceed, I want you to just maintain the same, the same sample of size k only, right? So what are the kind of properties you would want from a sample like that on an ongoing basis, right? So at any point in time t, right, when you have seen t elements, each element should have a probability of k over t of getting sampled. Why do you want this property? You want everybody to have a fair chance of being in the sample. Okay, and each group of k items should have a probability of 1 over t choose k, right, of getting sampled, because there are how many groups of size k are there? That is this much, right? 1 over t choose k, and each group should occur with this probability. Okay, and what you want to do is you want to satisfy this property at every point in time. Okay, does this seem doable? Just think of some numbers, right? Suppose k is 10, right? And you are moving from, let's say, 11th element onwards to the 100th element, right? At each point in time, I want you to satisfy that every element is picked with a probability k over whatever, right? 11, k over 12, and so on at those iterations time, and also this. Forget this for now. Let's say even this one. Can you think of a strategy to do this? Any ideas? Okay, let me make it simpler for you, right? Suppose k is 10 again, right? Just to take example, and you have seen 25 elements. Okay, let's say that you have satisfied this property, right? So your sample is such that your sampling strategy has been such that you have satisfied this, right? Now you see the next element. What should you do? This is the 26th element, right? Tell me, what is the obvious thing to do with respect to the 26th element? Good. Correct. Correct. How do you do it? So you are seeing the 26th element, correct? I have, correct. No, I have a sample of size 10, correct? Now I am seeing the 26th element, correct? Now, what will you do for the 26th element? Why half? What is the probability with which the 26th element should be there in the sample? You have the definition, no? This is the probability, right? What is K here? 10. What is T here? 26, right? So you are right, I am just guiding you. So you choose that element, you choose to keep it with probability 10 over 26, okay? Now what should you do with the other? You have 10 others, right? You have to throw out one of them, right? Can you think of some strategy to throw out? How will you decide which one you will throw out? Exactly. So you just randomly pick one of them and throw out. Okay. So the algorithm is simple. Okay. Of course, you will pick all the first k elements. After that, you are at the ith iteration. So you will pick that with the probability k over I. And if you pick that element, then you choose the one of them at random from the sample. You throw it out. Okay. So simple, right? Now the thing is that this actually satisfies all the properties that we were looking for, okay, and this is a very landmark paper, okay. I am making it very simple for you, okay. So can you think how would the proof strategy work? I mean, you are aware of many different ways of proving things in mathematics, right? How would you try to prove something like this? Induction, good, okay. So that's what we do, okay. So induction hypothesis, just as I told you, let's assume that we have satisfied this up to the nth ith element. We'll show now this calculation is very simple, okay. Fairness, right? Think about this. Okay. So you have, so each one of these elements that are in your sample will remain in the sample with a probability k over n. This is the probability with which the ith element gets selected, right? And it will remain in the sample with a probability k minus 1 over k, correct? Otherwise it gets thrown out. And the kth one itself will come in with the probability k over n, okay. So if you do the calculation, you will get that each element now actually has a probability of getting picked with a probability k over n. And as you see, I did not use anything other than just simple probability of the events. And this also is true for each of the group of the elements, okay. Exactly same induction hypothesis. I'll not spend much time on this because I think we'll lose time. I also want to ask you some questions, but this is shows that this is true for each group of elements, okay. Now we'll do a more interesting experiments. I don't know whether Manjunath talked about this. Did he talk about this? Okay, so this is a nice one. Okay, so let's assume that you are actually trying to hire a person for your company, okay, and you have n candidates, n applicants who have applied for that position, and you want to just pick one of them, okay. But the rule of the game is that you cannot test all of them simultaneously, okay. So they will come to you one by one according to some random order. You have to interview them one by one, and what happens is that you have a test which is very unique, okay. When you interview the candidate, you will get to know a score for that candidate, okay. Once you know the score, but I will not tell you what is the range of the score, okay. So the score could be 100, score could be 10,000, or even if you want to think that the score could be between 0 to 100, it could be 99.9, 99.99 and so on, okay. So the number of values that it can take is very large. What happens is, when you interview a candidate, you can either accept the candidate or reject the candidate. Once you reject the candidate, you cannot reselect that candidate, okay. So that's the rules of the game. And what you want to do is, you want to decide a point in time when you want to stop, right? So you want to say, okay, I want to select this candidate. Okay, you know n, and what do you want? What would you want to ensure when you do a process like this? What kind of a candidate would you like to select? The best candidate, right? So the question I am asking you is, can you think of a strategy, right, which maximizes the probability with which you pick the best candidate? Okay, I will give you one strategy which is a lousy strategy. Okay, so I know n, I will pick some position, okay, some position I, and I will say that I am going to pick the ith candidate. Okay, what is my probability of success of picking the best candidate? 1 by n. Good. So now you know that there is a way to succeed with a probability 1 over n. Okay, I want you to think of a strategy which succeeds with a probability much more than 1 over n, maybe say 10% chance. Do you think such a thing is possible, that I can devise a strategy wherein I can pick the best candidate? Think about it, right? Once I reject, I cannot call back the applicant. Okay, and I have n candidates, n could be really large, n may be 100,000. Okay, so can I succeed with a probability 10%, 1 over 10? Is it possible? No, you can talk to anyone only once, and once you talk to that person, you have to either stop or proceed. If you proceed, you can't call back that candidate. Okay.
We interview some of the candidates.
Okay.
We note down each of the rank or each of the ranks of
Hmm.
and then on the further interviews, if anyone achieves a rank which is greater than on the previous rank, then we'll select them. So
Excellent. Okay, can you just come and show that it works? Yeah, come. Good. That's exactly what I was going to do. So he has already come up with the solution. You will use reservoir sampling? Let's first hear his idea, then I will want to know how to use reservoir sampling.
if I'm taking the
Yeah,
candidates in
1 to n, you chose. It's a very good strategy, and so were you aware of this problem before, or you thought of this now?
I had a session study on maximum study.
Okay. Okay, excellent. See, Adirupa, I'm helping you prove that the sessions were useful.
So these are rankings of all the candidates.
Hmm.
And suppose I have interviewed till here,
Hmm.
and then probably I have interviewed this guy.
Hmm.
That seems to be better than whatever I have already seen.
This is the score, or this is the rank?
The score I have assigned for everyone. Like I have only interviewed till here.
Okay.
These are, even if I complete the interview for everyone,
Hmm.
I'll be getting these
Correct.
scores.
Hmm.
So I have already interviewed these 5 people
Hmm.
and rejected them.
You have rejected them. You have recorded 7 as the highest score.
7 as the highest score.
Okay.
Now here in the next 5, I get the higher score than whatever I have.
You got 8.
Yeah, I got 8. I'll go ahead and select this guy.
Hmm.
Or if I feel anything closer to 7, if I see, I'll select them.
Okay, let's say you picked 8, but in this case you failed, right?
Yeah.
So in this example you failed, but can you show that this actually is a good strategy?
Suppose if I get, I don't think it.
Okay, we'll show. It's actually a good strategy. Okay, we'll. Okay, so as he said, right, what we are going to do is we are going to reject the first half of the candidates. We will not select them. Okay, but what we will do is we will remember the best candidate amongst them. Okay, like he did. We remembered 7, but that's a slightly wrong example though. Okay, then after that we will select the very first candidate whose score is better than C. Okay, if no such candidate comes, we have no choice but to pick the last candidate. Okay, in which case we might have essentially failed. Okay, so what kind of condition do you want at this point in time, right? When will you succeed? Obviously, if you want to succeed, the top guy has to appear in the second half, correct? If that is not the case, you will not succeed. Correct? Is that clear? And since you are going to pick the candidate whose score is immediately better than C, right? What do you want here to make sure that you are actually going to pick the best guy here? You want the second best guy here, right? If the second best guy is here in the first half, and if the best guy is here in the second half, your strategy will definitely succeed. Are you convinced? And now it's very simple. Since it's a random order, what's the probability that the second best candidate appears in the first half? Half. What's the probability that the best candidate appears in the second half? Half. Right? These are independent, right? So, sorry?
Among the list of appearance worker, how will we knowing who is the first best?
We need not. That's the thing. That's the idea is that you don't need to know. Okay, this is a probabilistic experiment, right? So as long as the right things happen when you make random choices, your algorithm will succeed. The idea is you should make right choices, right? So here your choice will be right if the second best candidate appears in this half and the best candidate appears in this half, right? As long as that happens, you don't really need to know what is the range of the score, what are the scores, who are these people, nothing you need to know, correct? And the cool thing about this is that both the events actually occur with very high probability and they don't have a bearing on one another. Okay, so that's why you succeed with a probability 1/4. Forget 10%. With this very simple probability, this simple strategy gives you a 25% chance that you will pick the best candidate. Okay, and in fact the best answer here is 1/e, where e is actually the base of the natural logarithm. Okay, and the strategy is also similar. Instead of half, you will reject first n/e candidates and do the same thing. Remember the best candidate and then pick the next best candidate. Okay. So as I promised, I have not used anything other than simple definitions of probability and expectation. Yeah. So what we will do next before this is we will do one more example, or we will not do an example, we will do that as a problem. Okay, so what I want to do is, now I just want to show you that you can actually prove very powerful results in computer science using these simple techniques. Okay, nothing, not any deep mathematics, but simple counting and simple probability. Okay, and here is one example of a problem which people had been using for several decades, and a very nice sampling strategy was shown very recently. Okay, so have you heard of this problem, association rule mining? Anyone? You have heard. Yeah, tell me what do you know what, tell me what is association rule mining?
Actually, we have some features divided into
the best features of them one, which gives me the proportion which if we test the data, we can get the features out of it.
I do not completely understand. So you are saying you have a data, okay, and it's a table, right? Okay, there are columns you are calling as features, okay, and then there are rows, and then
By association group mining, we are taking out the best of the data which we can get from it.
okay. Anyone else? Have you heard of this problem? Okay, yeah.
For example, we have some data set. In that we want to find some rules that will relate each sample to some label. So we want to find some, for example, sentence that we can call as a rule, and if we apply that rule on the data set, so how well it will relate to the actual one. So that's
Okay, yeah, you are pretty close. Good. So that's the thing, right? So what are the kind of associations associated with a particular rule, right? So that's what you are trying to do, right? So who are the people who buy bread, for example, in a supermarket, right? So formally, what you have is let's say I'll take an example of a supermarket, right? There's a market which is selling many different items, okay, M items, I1 to IM, and there are many customers who are coming and who are doing transactions, okay. There are N customers who have come and done N transactions, T1 to Tn, okay. Each transaction is some subset of items that customer wanted, okay. T1 is something that this customer bought 2 items, this customer bought 3 items, this customer bought 3 items, okay. What we say is, suppose you look at any subset of these items, okay. In this case, maybe let's say you look at 1 and 6, okay. Frequency of that subset is the number of transactions containing X divided by total number of transactions. In this case, 1 and 6, this subset 1 and 6 has a frequency of 2 over 3 because it appears in 2 transactions out of 3, okay. 1 also has a frequency of 2 over 3, okay. And what association rule mining does is, it first of all tries to find out which are all the item sets that occur very, very frequently, okay, which are the items that people are buying together, okay. And then it also tries to learn a rule which I will not get into, okay. So let's just assume that we want to do this, right. So suppose I give you some theta, I tell you I am interested in items, set of items which are part of, let's say, at least 1% of the transactions, okay. What you want, so the question asked to you is to take this particular data and tell me all the subsets that appear in at least 1% of the transactions, okay. This is the frequent item set mining, and then on top of this, what you will also try to do is, if there are any, so this is a minimum requirement for anything to become part of a rule, and then you will also associate a rule saying that, okay, this subset of items, if it is there, then it also means that something else will be included. That's the association rule that you want to learn, okay. So the reason, as I told you, right, so this is a problem that is used in all kinds of fields. In science, people used to learn many different association rules between characteristics of different living organisms or different functions of functionalities of body, gene expression data. And in commerce, people try to find out what are the kind of transactions that are very popular amongst their customer base and so on, right. The problem, however, is that the algorithm that is used to compute this frequent item sets is a very costly process, okay. I will not tell you what it is, but it's a very costly process, okay. And and the data sets on which you try these, you want to find these things out are very big. For example, if you want to do this for the Walmart, right? So Walmart's just a weekly number of transactions is something to the tune of 200 million. If you want to do for the entire year, it's couple of 100 billion transactions over which you want to do this kind of experiment. You want to find such item sets. So the question really is, can you actually get as good frequent item sets as on the entire data with a very small sample of this data? Okay, and this is the only slide in which I will use something slightly non-trivial. Have you heard Chernoff bounds? You have not heard. Okay. So this is a very useful concept in designing randomization strategies. Okay. What it tries to tell you is, it tries to tell you if you have a random variable which is summing up of a set of let's say n different random variables which are independent, identical, okay, then Chernoff bound tells you what is the probability that the outcome of your experiment is very different from its expected behavior. Okay, so there is an expected behavior for this experiment. What is the probability that the actual outcome of the experiment is very different, right? Let's say 1 minus delta times of what is really the expected behavior, right? And that is actually this quantity, e to the minus delta square expectation of that experiment divided by 2. Okay, so this obviously, as your delta goes closer to 1, this number really becomes small and very small. Okay, it starts going exponentially small. That's the significance of this theorem or the bound. Okay, and we will show that we can obtain a very useful sampling bound for the association rule mining with a simple application of Chernoff bound. Okay, before that, for the problem at hand, let's try to see how to use Chernoff bound. Okay, let's say that you have this database of transactions and you are let's say you have taken a random sample. You know what is a random sample? So you just randomly sample at each step, okay, and this is actually called with substitution, meaning that you may get the same transaction twice. Okay, suppose you have taken a random sample of size S. Okay, how to bound this kind of an event, right? Let's say that its real frequency is fx, okay, and its frequency in the sample is f superscript s of x. Okay, what I want to do is I want to do something like this. What is the probability that this difference is not is very high, right, is bigger than epsilon? I want to bound this. How do I use Chernoff bounds, right? For that I want to use something like this, correct? Here what we do is that we will say that each so I'm taking S samples, right? Each experiment will try to see whether this particular element appears in the sample or not. Okay, and that will happen with a frequency fx, right? And we will say that this expected value of x is essentially the sum of the number of times this will appear, right? And so therefore the probability that this is greater than or equal to this is nothing but this expectation is greater than epsilon times the size of S. Okay, and you get some term like this, and where the size, as the size of this sample S increases, this starts going down exponentially. Okay, Ideally, you would like to do something like this, okay? So you want to take a sample S and report all these theta frequent items from this sample and not report anything else. Okay, so this is how a sampling strategy would work. Okay, but this is really not a good idea because there might be, you will have trouble with item sets whose frequency is very close to your theta parameter. So we will define an approximation to this problem which we call as epsilon cross item sets. What we mean is, instead of theta we allow items which are in this region also to be output. Okay, something which is not really at theta but very close to theta is also fine if you want to include it, but definitely you want everything here. You do not want everything here which is like low frequency. In this region you are willing to tolerate error. Okay, so for this I'll not present the proof of this, but using very simple techniques from probability and counting, what you can do is that you can show that a sample whose size is actually independent of either number of items or number of transactions, right? Neither m appears here nor n appears here, correct? And this sample size is sufficient to get us output which is almost equal to the output on the entire database. Okay, so this is fine. I'll not show you this analysis, but what we'll do is Adirupa had asked me to give some questions at the end of the thing. So we'll use next 10 minutes to solve 2 or 3 problems just to see how much you got out of this exercise. Okay, because I was not really anyway planning to keep it as a research talk. I would want any one of you to come and there are prizes, right, for solving, or okay. I will not ask you anything which requires any new thinking. Okay, it will be the same thinking using the examples that I have already shown. Okay, so the first question is, suppose I give you a graph. Okay, you already know what a graph is. The max cut in this graph is defined to be, some subset of vertices S and its complement S dash, such that if you look at all the edges in E, right, these are all the edges in E which are going from S to S bar. Okay, and what you want is, you want this size of this number of edges that are going across to be as large as possible. S, which gives you this, is called a max cut. Okay, so one property of this is that max cut is greater than or equal to number of edges divided by 2. Can one of you argue using what we did now in last 45 minutes? Think of the independent set example that we did. Any ideas? I can flash back. Okay, So something similar you have to do. Yeah.
Suppose we have less than number of edges by 2 in the maximum, then either A or B will have like more kind of thing. So we can actually include those and make the cut like smoother.
Good. That's actually a different kind of argument. It's called a local search. Okay. So that's good. That's good. But I want you to. That's correct. Okay. So that shows that as long as there is half of the edges are not part of this, you can always improve it, right? So that's called a local search heuristic. Okay. What is a local search heuristic? There is a very well known algorithm for this local search heuristic. What it does is you begin with some subset S. As long as there is one node that you can add to or remove from it, which improves the solution, you keep doing it. Okay, and you stop when you cannot do it any longer. And using your argument, you can show that it is at least half. Good, but I want a probabilistic argument here. Similar, actually similar. I'll do the first step of the solution. I want somebody to tell me what's the second step of the solution. Okay. So what I will do is I'll just pick some any random subset of size S exactly V by 2. Okay. Let's say that S is such that its size is V by 2. Okay. I'll put S here. I'll put S bar here. What can you tell me about what edges appear in this? Like now, look at every edge in the graph, and what can you tell about whether whether it is going to be part of max cut or not? Anyway, he gets that prize. Okay. Think of an E, right? When will it be there in the cut when I do this experiment? When both of them are in two halves, right? What is the probability of that happening? Half. So, what's the expected size if you add over all edges? Half the number of edges, correct? Which means there should be at least one cut of that much size, right? Okay. So this was one. Okay, now the other one. Suppose I tell you, okay, so this is space Rn, okay, Rn, and there is some object here, okay. Let's say, or if you want to think in R2 also, it is okay. Okay, I want you to get an estimate of its volume or area. How will you do it? Okay, good. Okay, she gets the other one. Now the third one, okay, so this is difficult. So we will do the following experiment that I will write. I can take 5 more minutes, Adirupa? Yeah. So what I do is I'll write two numbers on both my hands, okay, and they are going to be distinct numbers. They will not be equal to each other, and they will be positive numbers. Okay, so they are positive numbers greater than 0 and distinct. That much I will tell you. Okay. What you can do is you can ask me to show one of the hands, and I will show you what number is written on it. Based on that, you have to tell me whether which hand contains the larger number between the two. Okay. Okay. First of all, what is the minimum probability with which you can succeed? Half. Okay. So I want you to devise a strategy wherein your probability of success is strictly greater than half. I'll come to you. Try to think for a couple of minutes. Okay.
When you show me the number,
Hmm.
suppose you do it every day. So the probability that the other number is less than 10
Hmm.
will be 9 by 10.
Why is that?
Like,
It could be any number, right? I said real number.
oh yeah, that's what I'm telling you. You show me one number,
Ah.
just assume the range is 10. So the probability that that number might be lesser,
Hmm.
9 by 10. But then more greater probability that it will be greater. Right? So
No, but this could be any two numbers. I might pick 10.1 and then other number is, let's say, 10.2. Right? Assume that they are greater than 1 also. That probably will help you. Greater than 1, but it could be anything. Okay, you can always pick the. Why will that succeed? No, that actually depends on the two numbers at hand, right? So you have randomly picked one hand, you have seen it. Why is the probability that the bigger number is the other? No, as I said, I could have picked any two numbers of my choice, correct? 10.1 and 10.11 could be the two numbers. So you have to do something with the number you have seen, otherwise what's the use? Okay, see, in these kind of questions, even when we looked at the candidate selection problem, right? So you want to first don't think of probability. Try to think of what is the event that you would like to happen. Then you can devise a strategy, right? So when you see the number, what would you like your strategy to do? You have only two strategies possibly, right? Either to stick to the hand or switch the hand. What property should it have? Okay, because you don't know anything about the two numbers, right? You have only seen one number, but you want something about this strategy, some property, right? The property should be that the probability of rejecting the smaller number should be higher. The probability of rejecting the higher number should be smaller. Suppose you have seen the larger number, your probability of rejecting should be smaller. Suppose you have seen the smaller number, your probability of rejecting it should be higher. What should you do? So you have seen X and Y, right? Okay, let's say there is x and y, x is greater than y. Your strategy should be such that if you have seen y, your probability of switching should be higher. If you have seen x, your probability of switching should be lower. Think of a function which gives you that strategy. Exactly. That's all. So you reject that hand with a probability 1 over the number you have seen. So he will get the. You work out the details, okay, and make sure that it is greater than half, but that's what. So when you see the number, the strategy is pick a hand randomly, okay, and when you see the number, just reject it with a probability 1 over that number, and you will see that your probability of success is strictly better than half. Okay, thanks, I'm done.
Okay, thanks a lot, sir. I will myself love to hear more problems for you, but we are really out of time now. So whoever, 3